On occasion it is necessary or desirable to examine the structural elements and defects that influence the properties of materials. Some structural elements are of macroscopic dimensions, that is, they are large enough to be observed with the unaided eye. For example, the shape and average size or diameter of the grains for a polycrystalline specimen are important structural characteristics. Relatively large grains having different textures are clearly visible on the surface of the sectioned copper ingot shown in figure. However, in most materials the constituent grains are of microscopic dimensions, having diameters that may be on the order of microns, and their details must be investigated using some type of microscope. Grain size and shape are only two features of what is termed the microstructure. Optical, electron, and scanning probe microscopes are commonly used in microscopy. These instruments aid in investigations of the microstructural features of all material types. Some of these techniques employ photographic equipment in conjunction with the microscope. The photograph on which the image is recorded is called a photomicrograph. In addition, many microstructural images are computer-generated and/or enhanced. With optical microscopy, the light microscope is used to study the microstructure. Optical and illumination systems are its basic elements. From materials that are opaque to visible light, all metals and many ceramics and polymers, only the surface is subject to observation, and the light microscope must be used in a reflecting mode. Contrasts in the image produced result from differences in reflectivity of the various regions of the microstructure. Investigations of this type are often termed metallographic because metals were first examined using this technique. Normally, careful and meticulous surface preparations are necessary to reveal the important details of the microstructure. The specimen surface must first be ground and polished to a smooth and mirror-like finish. This is accomplished by using successively finer abrasive papers and powders. The microstructure is revealed by a surface treatment using an appropriate chemical reagent in a procedure termed etching. The chemical reactivity of the grains of some single-phase materials depends on crystallographic orientation. Consequently, in a polycrystalline specimen, etching characteristics vary from grain to grain. Figure B shows how normally incident light is reflected by three etched surface grains, each having a different orientation. Figure A depicts the surface structure as it might appear when viewed with the microscope. The luster or texture of each grain depends on its reflectance properties. A photomicrograph of a polycrystalline specimen exhibiting these characteristics is shown in Figure C. Also, small grooves form along grain boundaries as a consequence of etching. Because atoms along grain boundary regions are more chemically active, they dissolve at a greater rate than those within the grains. These grooves become discernible when viewed under a microscope because they reflect light at an angle different from that of the grains themselves. This effect is displayed in Figure A. Figure B is a photomicrograph of a polycrystalline specimen in which the grain boundary grooves are clearly visible as dark lines. When the microstructure of a two-phase alloy is to be examined, an etchant is often chosen that produces a different texture for each phase so that the different phases may be distinguished from each other. A more recent and extremely useful investigative tool is the Scanning Electron Microscope, SEM. The surface of a specimen to be examined is scanned with an electron beam, and the reflected, or backscattered, beam of electrons is collected, then displayed at the same scanning rate on a cathode ray tube, similar to a CRT television screen. The image on the screen, which may be photographed, represents the surface features of the specimen. The surface may or may not be polished and etched, but it must be electrically conductive. A very thin metallic surface coating must be applied to non-conductive materials. Magnifications ranging from 10 to in excess of 50,000 times are possible, as are also very great depths of field. Accessory equipment permits qualitative and semi-quantitative analysis of the elemental composition of very localized surface areas. In this part you can see all parts of SEM.
Components of the microscope are column for electron beam generation, specimen chamber, vacuum pump, monitor, and control panels. She can open the cover plate of the specimen chamber. Together with the cover plate, the stage pans forward. Now different specimens can easily be placed on the round stage. The filament of an old used light bulb, part of a welded tube on a sample holder, a small cobalt plate, and a golden piece of jewelry. All specimens are assembled and we are ready to start. The material tester carefully closes the cover plate. The part is the so-called column. It is used to generate an electron beam. The lower part consists of the specimen chamber with cover plate. In the longitudinal section, the flange leading to the high vacuum pump is visible at the bottom. Thereby, high vacuum is generated inside the whole microscope. The round specimen stage may not only be moved to the left and to the right, but likewise in all other directions. It may also be tilted and rotated. All samples to be investigated are placed on the specimen stage. To create an electron beam, a V-shaped thin tungsten wire is used, the so-called thermionic cathode. Heated up by electric current, it emits electrons into the vacuum, indicated by small dots. Below the cathode, a metallic disc with a central borehole is installed, the anode. The anode is connected with a positive pole of a high-voltage source, the thermionic cathode with a negative pole. Further necessary components have been omitted for the sake of simplicity. The strong electric field between cathode and anode accelerates the electrons downwards. These electrons are called primary electrons. They form a broad, diverging beam which hits the specimens and the stage. But this way, the beam of primary electrons is not useful yet. An electromagnetic lens focuses it finely on the specimen surface. At the point of incidence, primary electrons knock out electrons of the sample material. These knocked out electrons are called secondary electrons. Additional components are necessary: electromagnetic deflection, raster scan generator, secondary electron detector, abbreviated as SE detector, and computer with monitor. The basic principle of the scanning electron microscope is to detect the secondary electrons and use them to build up an image. To increase the number of detected electrons, a positively biased grid is placed in front of the detector. The grid attracts the secondary electrons and leads them to the SE detector. And this is the way to generate a magnified image of the sample. The raster scan generator directs the electron beam to the left rear part of the sample and stops there for a short time. The number of secondary electrons is recorded in the SE detector. The signal is amplified and displayed as a dot at the top left-hand corner of the monitor. The electron beam pans slightly to the right, stops again. The measurement is repeated. In the same way, the next points on the sample are dealt with. The principle is, many recorded secondary electrons lead to a bright image point, few electrons lead to a gray image point, and none at all to a black one. An entire row is covered in this way. Then a second row, until finally a rectangular area has been scanned and an image appears on the monitor. If not only a few but many image points are used in the raster scan, a natural-looking image of the specimen surface can be seen on the monitor. When the fast electrons of the electron beam, the primary electrons, reach the surface, they knock out electrons of the specimen material. These are the secondary electrons used for image formation. What happens in detail shows a schematically drawn atom from near the surface. Just like any other atom, it consists of a positively charged nucleus and negatively charged electrons. The electrons stay in energetically well-defined shells around the nucleus. A primary electron comes from above and accidentally knocks out an electron from the K shell of the sample atom. A vacant place remains, as indicated by the yellow circle. This state is unstable. An electron from the L shell fills the gap and the energy difference is released in the form of a characteristic X-ray photon. This X-ray photon is called characteristic because its energy is quite characteristic or typical for the particular element. Now another transition follows. And finally the atom repairs itself with an electron from the vicinity, a free electron. So X-ray radiation is generated during the operation of the scanning electron microscope, namely X radiation, which is characteristic for the chemical elements present in the sample. If the energy and the intensity of the radiation are measured with an X-ray detector, then the chemical composition of the sample can be determined. Here the typical X-ray spectrum of the piece of jewelry builds up. Chemical analysis is then carried out using sophisticated methods with the help of a computer. Certain limitations must indeed be minded, but it's definitely a fine method, and above all, it is completely non-destructive, and even very small spots on a sample can be analyzed. And what has happened to the small cobalt plate, which was one of the samples? It was used to calibrate the measurement. This means to adjust it finely. The chemical analysis is finished now. Our piece of jewelry is genuine. The gold content amounts to about 70%. The balance is silver and copper.
Scanning probe microscopy. In the past decade and a half, the field of microscopy has experienced a revolution with the development of a new family of scanning probe microscopes. The scanning probe microscope, SPM, of which there are several varieties, differs from optical and electron microscopes in that neither light nor electrons are used to form an image. Rather, the microscope generates a topographical map on an atomic scale that is a representation of surface features and characteristics of the specimen being examined. Some of the features that differentiate the SPM from other microscopic techniques are as follows. Examination on the nanometer scale is possible inasmuch as magnifications as high as 10^9 are possible. Much better resolutions are attainable than with other microscopic techniques. Three-dimensional magnified images are generated that provide topographical information about features of interest. Some SPMs may be operated in a variety of environments, e.g., vacuum, air, liquid. Thus, a particular specimen may be examined in its most suitable environment. Scanning probe microscopes employ a tiny probe with a very sharp tip that is brought into very close proximity, i.e., to within on the order of a nanometer, of the specimen surface. This probe is then raised or scanned across the plane of the surface. During scanning, the probe experiences deflections perpendicular to this plane in response to electronic or other interactions between the probe and specimen surface. The in-surface plane and out-of-plane motions of the probe are controlled by piezoelectric ceramic components that have nanometer resolutions. Furthermore, these probe movements are monitored electronically and transferred to and stored in a computer, which then generates the three-dimensional surface image. These new SPMs, which allow examination of the surface of materials at the atomic and molecular level, have provided a wealth of information about a host of materials, from integrated circuit chips to biological molecules. Indeed, the advent of the SPMs has helped to usher in the era of nanomaterials materials, whose properties are designed by engineering atomic and molecular structures. This figure is a bar chart showing dimensional size ranges for several types of structures found in materials. Note that the axes are scaled logarithmically. Likewise, the useful dimensional resolution ranges for the several microscopic techniques discussed in this chapter, plus the naked eye, are presented in the bar chart of figure. For three of these techniques, SPM, TEM, and SEM, an upper resolution value is not imposed by the characteristics of the microscope and, therefore, is somewhat arbitrary and not well defined. Furthermore, by comparing figures it is possible to decide which microscopic techniques are best suited for examination of each of the structure types.